Exascale is something that's been looked at for about 9 years at least in terms of what the issues are. But the project that I'm pleased to be director of now just started last fall, essentially. And as it happens, it was just last Thursday, July 28th, that it received the stamp of an official large Department of Energy project. Now, that's just boring bureaucracy stuff, but to be labeled an official project meant a lot of reviews by many independent people about our plans and so on. Now, we're still in the very early stages, but I will tell you where we are and what we're trying to do. Tomorrow, for dinner, Doug Cothy, who is in the project as well, will tell you about some of the applications, both the issues in developing applications for Exascale and something about the applications themselves that we've been looking at. So it'll be a companion dinner talk. Now, I suppose that most of you know this, but since I used to be a mathematician, I really wanted to get into definitions here. So we're saying the Exascale project, right? Exascale computing project. We didn't say the exaflops computing project. So, peak speed is traditionally has been measured by flops. And so that's, how many floating point operations you can do if you keep everything busy, all the functional units, assuming that somehow magically the data is ready to be operated on, which usually it isn't. You have no cache misses, everything works perfectly. And so exaflops would be 10 to the 18th floating point operations per second. But, in reality, we only get a small fraction of that. Some major applications have gotten 50, 60%, but typical is 10 to 20%. And many are at 1 to 3%. So using the peak flops doesn't seem like the right thing to do. And so we're using a less precise definition of, our metric of exascale. And so what we decided to do, because in the end what really matters is how fast does a real application run, how many minutes or hours does it take, wall clock time. So for Exascale, we're saying, well, if you have a 10 petaflops system today, like Mira, and you're running a given application at a certain speed, that with an Exascale system, it should run 100 times faster if it's the same application. So that sounds nice and tidy. Unfortunately, usually when you go to a system that's 100 or 1,000 times faster, you don't normally solve the same problem faster. What you tend to do is to solve more complex problems or problems with finer grain resolution. So, for climate modeling, instead of, a 4-kilometer grid, you might have a 1 kilometer or half-kilometer grid. So it's not the easiest thing to really measure in any reliable fashion. But that's reality, and so just letting you know that's what we focus on is sustained speed for real applications, how they're doing on today's systems, and how they would do on the systems we are creating over the next few years. Now, computing, to my delight, computational science, simulation and modeling, have gotten to the point that the President of the United States issued an executive order just a little bit over a year ago, July 29th of 2015. If you'd like to read the exact executive order, here's the URL for the announcement. It says a number of things. The ones that I picked out is wants to maximize the benefits of high-performance computing for U.S. economic competitiveness and scientific discovery. And it's a multi-agency oriented executive order, but in particular, Department of Energy, within this National Strategic Computing Initiative, has the responsibility that two parts of DOE, the Office of Science that I talked about a little bit in my earlier talk, And the part of DOE known as the National Nuclear Security Administration, the one that worries about the health of the nuclear weapons stockpile, that'll be a joint program between the two sides focused on advanced simulation, doesn't say hardware, through a capable exascale computing program emphasizing sustained performance on relevant applications. So that's what matters. What can you do with applications? So what DOE decided to do is to create this partnership and have a formal project. So this exascale computing project is a 10-year project, and it's led by people at the DOE laboratories. As you know, I'm from one of those laboratories. But in particular, the leadership team that we've put together has people from 6 of the DOE labs. So the leadership team has people from Argonne, from Berkeley, Oak Ridge, Los Alamos, Livermore, and Sandia National Laboratories. And now in terms of executing some of the work, most of the 17 national labs that I mentioned earlier this afternoon are likely to take part in it. And although it doesn't say it on this slide, also people from academia, universities, and industry. And this project will be collaborating with the facilities that operate the most powerful computers. So one of them is the Argonne Leadership Computing Facility that many of you will see next Saturday. Another is Oak Ridge. Another is NERSC. And others at Los Alamos and Livermore. So those facilities, after all, are going to be the ones that buy the systems that are developed, install them, and operate them. So we're working very closely with them because they're one of the customers. So, I mean, we've been doing research on exascale-related issues for years. Why do we need a project? Well, for one thing, things have gotten more difficult. You're all aware of this, but I'll remind you that there are technology and physics limits that mean it isn't business as usual as it has been in the past to go from gigaflops to teraflops and teraflops to petaflops, which certainly pose many challenges, but to a large extent it was business as usual. But here we feel to be successful we have to take all aspects of the ecosystem and have them work together and develop together and feed off each other. So co-design. The applications have to identify requirements for the kinds of applications you want to do at exascale, not necessarily today's. What requirements in algorithms, in memory sizes, in maybe different kinds of functional units? So that'd be co-design for the hardware. But also, when it comes to algorithms, it'd be co-design for the software libraries. And we might be able to influence some of the hardware features over the next few years as well. On the other hand, the hardware, much of it is already determined, and so that's passing requirements to the software libraries and the software tools and the applications. So co-design is a big part of this project. For that to happen, you can't just hope that people talk to each other. They have to be in the same project and be orchestrated to talk to each other and exchange requirements and then do something about them. So that's the integrated planning and execution. One of the devices you use is you have to have milestones probably every quarter for these software projects and hardware projects, but some of them can be joint milestones. So if an application says, I need a new, I'll say, fast Fourier transform implementation for my kind of application, then somebody in a mathematical software library team may create it, but then they have to have a joint milestone that actually tests to see what was created really works for that application, and when it doesn't, probably won't the first time, then you go back and figure out how to make things work together. So that's part of it. Another is to have people, say from the software part of the project, spend some of their time as part of an application project. Because co-design and integration usually works best when people work together. not just passing emails to each other or white papers. So that's why you have to have the rigor of a project to get something like this done. So as a quick reminder of the things that I alluded to, that it's not business as usual on the hardware front, is that because the NARD scaling pretty much petered out in 2004, you can see that although the number of transistors keeps growing, pretty much along the Moore's law for a bit longer, that when you get to single thread performance, to the frequency, those are pretty much stalled out. And so that means that if you want 1,000 times more power in computing, you have to have roughly 1,000 times more pieces put together. You can't count on faster ones. Now here's one way to think of it. As we went from gigaflops to exaflops via tera and peta, so first, to go from giga to tera, about 32 times of the speed increase came from, I'll say, transistors for short, but still an equal amount from more parallelism. And then when you move to peta, most of the speed up came from parallelism, and a rough estimate is for exaflops, essentially all the speed up will come from parallelism. And so think of yourselves as writing programs for a system that has this incredible amount of hardware parallelism. I mean, never mind the 750,000 cores and 4 threads in each core for Mira, which means you've got 3 million pieces of hardware you could be using simultaneously. What if you have to go many more? How do you program that? How do you debug it? How do you even measure performance on it? So a committee was convened as a subset of there's a federal advisory committee for the Department of Energy Advanced Scientific Computing Research Office. And so that advisory committee convened a subcommittee to identify the top 10 technical challenges for Exascale. And so you don't need to read all the words, plus you can get these slides. But energy efficiency is one. I alluded to it earlier today. If we were to build an Exascale system today with today's technology, it might be 200 to 300 megawatts of power needed. Well, maybe not that much, maybe only 150 megawatts. It's still an awfully big bill, and that's not the whole picture. Not only when you're using the 150 megawatts, but do you have any idea of what it costs to install a megawatt in a facility? That's usually over $1 million per megawatt. So just to install the capability of having that much power in one room is very expensive. Interconnect technology. There are all these pieces that you want to connect in a way that they act as one efficiently. Memory technology, although I'm not going to dwell on it in this talk, the ratio of floating point operation speeds to how much memory is available has been tipping over to more and more flops and less bytes. And that's not very good for applications development. And then system software has to scale. It doesn't always just by itself. Programming systems, data management gets to be more and more important. Algorithms have to be addressed and redone. New kinds of algorithms as well, as people do more and more things like deep learning. Resilience is likely to be an issue, not only because there are so many more parts, but because of the feature size being smaller and smaller, there might be more silent errors. So how do you even detect that you're getting the wrong answer? Well, there are ways to do that, sometimes algorithmically by internal checks, but it's another big challenge. And then productivity, it's hard enough now to write big applications for the big systems. What about for the exascale systems and for the kinds of applications you want to solve on those systems? So can we hope to come up with better programming models and approaches and software engineering to increase the productivity of the relatively few people who are involved in this kind of work? Now, Executive order that created the National Strategic Computing Initiative, uses the phrase capable exascale computer, and that's to emphasize that it isn't just a lot of flops in hardware in a room, but something that here we're using 50x as the multiplier for, let's say, a 20 petaflop system or 100x for Mira, so it can solve science problems that much faster, that it doesn't cost too much to provision it with electricity. So a power envelope between 20 and 30 megawatts is still a lot, but at least it's much less than hundreds of megawatts. It's sufficiently resilient that a user can think of, well, I've got maybe a week in between when there's a fault that affects the running of my job. So I'm not saying that it's a week in between any faults, just what a typical user program would experience. And then a software stack that's aimed at supporting a broad set of applications, not just, say, a few computational fluid dynamics applications, important as they are. We want to be able to serve a broad amount of science. You'll see a glimpse of that in a few slides. So that's what we are aiming for in this project, to do this in 10 years or less, and for many different applications. So the way we've structured the project is in 4 areas. I mean, I talked about holistic and having to worry about the whole ecosystem. So this is one way of thinking about it. So application development, so science and mission applications. The software technology, so we're aiming to create a scalable software stack. Hardware technology, we plan to let contracts with hardware vendors, hopefully very soon, in a couple of months, aimed at giving those vendors the opportunity to explore new features of hardware that may result in a better system that can be built starting a few years from now. Better system for scientific applications of the kind that we care about. And then exascale systems, think of it as the facilities. I mentioned that the facilities would be tightly involved in this project, and so the facilities people are involved here too. Now they have their own software requirements, by the way. They have to have job schedulers, and they have to have ways of measuring and identifying faults and measuring I/O and worrying about all those things. So they're part of the project. And so all of those are working together. So here's, without any detail, but just a sampling of what we consider to be NSCI critical applications. So in national security, of course, there's the nuclear weapons stockpile, which is referred to as stockpile stewardship. This is a program that was initiated by President Clinton in the early 1990s, when he said no more tests, even underground tests of nuclear weapons, but instead you have to use computing and simulation and expertise by weapons designers to determine, is the nuclear weapons stockpile still usable? If we ever had to use it, would it work? Decision support for all kinds of decisions, battlefield command, counterterrorism. So some of these, you can imagine, are not the traditional flops-oriented solving partial differential equations. Communication, cyber defense, signals intelligence. For economic competitiveness, there's a lot. Energy production, for example, wind energy. So one of the projects that's being considered is better design of wind farms. It turns out that, as you can imagine, if you have row after row of wind turbines, the ones that are in front get the clean air, but the ones behind get the turbulence from the disturbance of the first one, and so on down. And so you can lose, it's estimated, maybe 30% of the potential energy just from that. But what if you can site the turbines so that it minimizes that interference? So that's one example of energy production. Advanced manufacturing, digital engineering, drug design obviously is huge. And personalized medicine. that's something that, believe it or not, high-performance computing can really affect and enable. And there are some specific projects that are being considered for that already. Healthcare, business analytics, of course. Once you get to a certain size, you need a lot of computing and data analytics power, e-commerce, social networking even. Although I don't have it here by that title, urban science is something that a number of big cities around the world has started to do. Barcelona, Spain happens to be one that's pretty advanced in that. I know there's at least, I think there are two students, two participants from Barcelona. I know at least one. So even, and Chicago, the city of Chicago is also doing that, as is New York City and others. So even that can require exascale. And then the usual, scientific discovery. Climate science, which of course has impacts on economic competitiveness and national security as well, because of violent climate events, for example. Being able to predict more reliably the path of hurricanes can give cities more time to do something about preparing. Fusion, materials genome, particle physics, of course, neuroscience, weather prediction as opposed to climate science, and genomic discovery. So there are specific projects that have been formulated to address each of these as well as some others that are queued up, if you will, to take advantage of exascale. That's the exciting part. And tomorrow, you'll get to hear a lot of interesting detail about it. I wish I could do it. I'm a little bit frustrated by it, but Doug Cote, who's the head of the applications focus area, where I say application development, he leads that part. He has a deputy, Bert Still from Lawrence Livermore. Software technology, I might mention, is led by Rajiv Thakur, whom you will meet tomorrow. He is one of the key people for MPI and developed MPI-IO. And he has a deputy, Pat McCormick, from Los Alamos National Lab. Jim Ang from Sandia, Albuquerque, leads hardware technology, and his deputy is John Shelf from Berkeley. And finally, Exascale Systems is led by Terry Quinn from Livermore National Lab, and her deputy is Susan Coughlin from Argonne Leadership Computing Facility. So, a little bit more detail on what the applications focus area that Doug leads involves. Well, the idea is to fund development teams that have identified specific challenge problems that they think might be feasible to address at exascale. So it isn't just saying we'll do better, it's a very specific challenge problem. And those teams will be required to follow software engineering practices. And part of their job will be to interact with the hardware and software people in a very intimate, continual way about their requirements and getting them solved. And as I mentioned, executing milestones jointly. In addition, we intend to fund some co-design centers, in this case not aimed at a specific application, but on methods that tend to be used by a number of applications. And the ones that would be chosen would be derived from knowing which applications we are supporting in the first place. So an example would be particle and cell methods or adaptive mesh refinement that are used by many different kinds of applications. And then one part is developer training. And that's why this program that you're in, the ATPESC, is part of the Exascale Computing Project, because it's under this rubric, developer training, that we're funding the project this year. And I'll say a little bit more about it later on. So that was applications. Well, software you can think of as the bridge between the applications and the hardware. So I'm using as a placeholder on the right for hardware that that graph I showed earlier about the behavior of transistors. And on the left, I just have the cover of a number of reports from workshops that took place a few years ago, each of which was on a certain domain. So there was one on material science, one on high energy physics, one on fusion, chemistry was another one, and so on. So software is the bridge. And so I had the little arrows going in various directions because it has to both provide and receive requirements. And so our conceptual software stack that we aim to create has all these pieces to it. Now, some of it will be developed and delivered in part by industry, the companies that build the hardware that we buy. But a lot of it, traditionally, people at universities and national laboratories have developed and will continue developing. So along the top, we have, so it's not a traditional software stack in that instead of having applications at the very top, we chose to put application correctness, visualization, and data analysis above applications because, in essence, applications require those things that are above it. And then below are the usual programming models, math libraries and frameworks, tools. You can probably read all these on your own. As you get lower and lower, like the node operating system, low-level runtimes, we'll be working very closely with industry. One of our dreams is, for example, to try to converge on a common set of runtimes with APIs so that all the things above it don't have to deal with different runtimes depending on what you're doing or what piece of hardware you're on. And then at some point you get to the hardware. Now on the right and the left I have vertical bars, resilience, and that's to indicate resilience is everybody's business. It's part of the hardware. There are hardware features aimed at resilience, but then all the other software pieces, and it includes the applications, have to worry about resilience. There's no one tool that will give you resilience. And on the right, where it says workflows, again, more and more applications have complicated workflows where you might be getting data in real time from a big particle accelerator. You stream it to another system to do some of the analysis, but then you end up at an exascale system, or today a petascale system, and do some analysis. And then perhaps you do data analysis or visualization on either within the big system or in another one. And so you have a workflow that needs to be managed. And so those, again, affect many parts of the software stack. And we see that as a growing type of application that needs complex workflows. So we will be investing in those. Along the bottom, you notice I pointed out that of those top 10 challenges, software stack is aimed at addressing quite a few of them. You can refer back to what 4, 5, 6, 7, 8, and 10 were, but that's 6 of them, 6 out of the 10. Now, I said it's a bridge, so let me continue with that metaphor. One of the problems is, there are some interesting new ways of programming systems and all the software stack, but a lot of applications that already exist have hundreds of thousands or millions of lines of code, and we have tools that are not the greatest, but compilers and debuggers and so on that seem to work. So we can't afford to abandon all of that and switch immediately to a new set of programming models and all the tools. It takes years to get them to work properly. It takes years to learn how to use them and to develop them. And so, the metaphor that I use is when, the old bridge over San Francisco Bay was damaged by earthquake, and you really need to build a new one. Well, they fixed the old bridge, and it kept running for years while they were building the new one. So now there's a nice new one. You see, it looks much nicer. Still has a lot of the features of the old bridge, doesn't it? So my point is, we will be transitioning the software, the methods, as much as possible in a gradual way. And some things will be there even 10 years from now. Some things are just not going to go away. But a lot of things will change. Then hardware technology. Traditionally, we in the high-performance computing community have worked with companies to help design systems that are better suited to science and engineering applications. So this has gone on from the days of Avadac that I showed you this afternoon at Argonne and before. The IBM stretch at Los Alamos is another example. There are many, many examples. But now it's gotten to be more difficult as we use more and more commodity parts. However, companies are willing to talk to us, and if we pay them to explore new things, they often do come up with some things that are beneficial to us. And so, in fact, we issued in early June of this year a request for proposals from the hardware vendors for coming up with better ideas and designs for both nodes and entire systems that could be put into exascale hardware in a few years. We received the proposals last week, I believe. I think it was Monday of last week. My schedule's a little bit of a blur. But very recently, we got proposals, and in August, we will be evaluating them. And so we're aiming at addressing top 10 challenges, 1, 2, 3, and 9, hopefully through the ideas that are developed by the contracts that we will put in place for these proposals. Another aspect of the hardware technology activities of the project is design space evaluation to use abstract machine models and architectural analysis capabilities so that as new ideas come up, there's a way to get a little bit of confidence of how well would they work on real applications before anything is implemented in hardware. Some of it could be implemented partly in FPGAs. So that's hardware technology activities. So I said at the very outset this is a project, and so projects have work breakdown structures, and I do not expect you to read all these words, but it just shows a level of detail of how we're organizing things. But in particular, I want to show that developer training and productivity is a work breakdown structure element under application development, and you are there. That's at best. That's part of it. Now, we intend to do additional things, but this is the first activity that we're funding from the project. So I wish we were further along so I could give you some results, but we do have a lot of application proposals that we hope to give the green light to very soon. We have a lot of software technology proposals. I mentioned we have hardware technology proposals. So we're poised to issue a bunch of contracts and get the work going soon. And we want to fund a lot of applications of different kinds. A full-scale ecosystem, hardware design, and work with the facilities with a lot of emphasis on co-design and integration. And I already mentioned the work will be done by people at the DOE labs, but also academia and industry. Now, in a project, you also have to identify risks. And so one of the risks, which has a catchy number, 2001, it's not a reference to Space Odyssey, it just happened to fall that way, is literally, it says, unable to recruit and or retain qualified staff needed to execute the research and development for this project. This is a big project. We need a lot of people. Certainly there are plenty of people at the national labs and universities in place today that hopefully, well, we have evidence they are interested in participating in the project, but we will need more. And so those of you who are taking this training program, you may well be intrigued by the project, either today or when you're a little bit further along in your career. You might end up working for the project. It's a 10-year project. I'm biased. I think it's a very exciting project. I'm really pleased to have the opportunity to get it going. But as you saw, it has all kinds of activities. So if you're interested in hardware, all kinds of algorithms, applications, software tools, methodologies, there's something in there for everybody. So tomorrow, Doug Cothey, as I've already mentioned, will give a talk on the ultimate payoff. What really matters is enabling new applications to do new things couldn't be done before that help our society and the world. But I didn't say much about the applications because you've got to talk tomorrow. That's all. Any questions? Be Be glad to field questions. Yes?
So we talked a little about the runtime, interoperability, and abstraction of the hardware. But if we take this a little bit higher in the application, like choosing an algorithm that fits a given hardware, will any of the project will address this problem of how we're gonna create an application running in, for example, in Argonne on a system that's uniform to another system in Oak Ridge that's heterogeneous.
So let me paraphrase, make sure I understood your question. Are you saying how do you achieve portability?
Yes.
Thank you for asking that question because I didn't include it here. And that was a mistake on my part, I guess. So back to project speak. So when you have a project, you need to be able to measure it. And so you have things that are called key performance parameters. One of them is actually aimed at, have we achieved performance portability? So although I didn't say it, part of the applications development approach and a lot of the software technology in that software stack that we hope to develop will be aimed at achieving, I'll say modest or moderate portability. Now you can't expect perfect portability where you make no changes whatsoever, but it should be a goal to make relatively few changes. So we don't have the final version of these key performance parameters yet because the project is scheduled to do those in 2019. But right now the working definition is that an application is performance portable if it runs on two different systems, and that's running real applications, real problems. The difference in time from one to the other is no more than a factor of 2, and there's minimal changes of the code. So now minimal, of course, we'll have to lock down. Does that mean 5% of the lines of code? That's probably too much, actually. Or because you don't want the NIFDEF at the very top that says, okay, I'm running on Titan, I'm running on Mira, and so it's a completely separate software stack. Now that's a very ambitious goal to achieve performance portability, but it's a very important one. And I think in the process of designing applications and implementing them that way, it should also make them easier to maintain and to enhance because it should be more structured and you have the abstractions at the right levels, hopefully. Thank you. Any other questions? Yes?
So this is, you already said this is not the first Exascale project which actually exists. So how do you actually, how well is the, how deep is the cooperation with other projects such as PRESA or so the EU funded a lot of Exascale projects. There's Exascale projects on nuclear fusion, for example, which are more specific. So how is the interaction with other projects planned into this?
So you touched on several different kinds of things. For example, you said fusion exascale. Well, that's a specific application. And under scientific discovery, you'll see fusion science. And so it's conceivable that one of the applications that we have proposals for in hand, maybe they will be funded. So with specific domain applications of exascale, many of them we may fund in part. So let's see, a good one to talk about would be climate science. A few years ago, the Department of Energy decided to start its own code project, still collaborating with NCAR and the National Science Foundation, but to develop a new climate code aimed at exascale. So that's an existing project. It's a good one. It's a pretty big one. And so it is possible that we will fund an additional activity within that project to cover something they have not yet been able to cover. But then they'll also have the benefit of working in this context of co-design with the rest of the project. Now, for other world regions like the European Union, they haven't really had an exascale project that's comparable to this project. They've certainly had exascale R&D activities, absolutely, and they will continue to do that. And there is talk of the European Union having a project that's really absolutely aimed at creating an exascale system, and that may well happen. And I could imagine some collaborations as that project gets going and we're getting going, that we would find some areas of common interest. Now Japan has an exascale project in place, and we being people in the Department of Energy National Laboratories already have collaborations with them on certain aspects, especially in the programming and system software stack. And that's been going on for several years. So we're open to collaboration where it makes sense. But we won't cover everything, and I hope that there's funding by others for related things. There's a lot of work to be done. The more the better. Thank you.